Hi, welcome to the next video in a series of videos building a modular bench power supply. In the previous videos we've already looked at the power stages, voltage references, and some fundamentals of operational amplifiers, and we've tested effects of varying power, noise, and also heat on some of those circuits to see how they work. None of it's yet been put into a full power supply. We're slowly building up towards that. So what are we going to do in this video? Well, so far we haven't covered how you can actually see what you're outputting. So we need some kind of output display for the power supply. So what I want to show you today is some low-cost panel meters that you can buy. You can get these as self-contained units. The ones I have run off of a 5-volt supply. They have differential inputs, and you'll see why that will become important as we go through the video. And they have a full-scale range of 200 millivolts. So the reason I chose these as opposed to ones with higher volts is because I can actually just put a resistor divider network on the inputs to these to make anything up to, if I wanted 2 volts, 200 volts, 20 volts. It's just a case of having the right resistor divider network. Also, because for current sensing I'm using 100 milliohm or thereabout current sense resistor, then for 1 amp I'm only going to have 100 millivolts. So for 2 amps I'm going to have 200 millivolts dropped across one of these panel meters. Now that's all I'm going to go to in this particular one is a 2 amp range, because I'm aiming this at really the student beginner power supply where you wouldn't necessarily want to have very, very high currents. Now, of course, if you do want to go higher currents, then it's just a case of putting a divider across the sense resistor, so that you can maybe, instead of putting 100 millivolts per amp into the display unit, you could put, say, 10 millivolts. So you do a 10 to 1. That way you would have a full-scale reading of, say, 20 amps instead of 2 amps. Anyway, the units that I got from Element 14, and these tiny little displays, they're quite good. They're basically 3.5 digit. They're very simple. They have a couple of, you've got little plug-in connectors on the back, so you could put them on a breadboard for experimentation very easily. I'll link the Element 14 part numbers in the text part of the blog when I post it. But you can get these readily from Element 14 or even on eBay if you wanted to. There are lots and lots of different panel meters that have 200 millivolt input range and various other ones, and you can even get 4.5 digit ones as well. They're relatively inexpensive. This one on the back of it has got a trim resistor so that you can adjust the voltage reference. You can see it just tucked in there. I've done a little bit of playing with this already, and I found them to be spot on, so I haven't had to adjust them. They also have a little bezel that comes with them. Let me just grab the box a second to show you. So you can do a cutout. They have a bit of edge around them, so you don't have to be perfect as long as you're inside that box. And the meters come with a little metal clip, so you just push it on the back to make it secure. So it's very simple to put into a panel if you want to for your power supply. They work well, and they're easy to hook up. So without messing around any further, let's get to the breadboard and hook it up, and I can show you what they can do. Before I plug it in, I just wanted to quickly also point out, because it's going to be hard to show you once it's on the breadboard, is it's very important to make a note of where pin 1 is. On these particular panel meters, they have a little arrow here which indicates pin 1 on the bottom, and it's just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 up the other side. Okay, just wanted to point that out before we go and blow something up. Okay, to start with, we're going to have a look at what's actually in the panel meter. So this little diagram that I've got right here actually shows you what is inside the panel meter. So we have the LCD display, which is the, as I said, 3.5 digits. And the ones I have, as I said, they're powered off of 5 volts. So what you have in here is a 5-volt supply with a DC to DC converter, because you need a negative voltage for the op amp, because, as I said, these meters will do plus and minus voltages as on their inputs. You have a decimal point control. All you do for this input pin is you just simply ground it and it will put on the relevant decimal point. On the other side here you have a voltage reference output, which is basically driven off of the 5-volt supply, off the analog common, and 5 volts, and it's just got an adjustable pot on here that can adjust the voltage reference. That's the one I showed you on the back of it before, and it feeds out and then back into the A to D converter. Now this 5 volts, don't think that it's the one that you're pumping in. We've got this DC to DC converter as well, so I'm not sure of the exact internal circuitry, but these things appear to be quite stable. I will try and adjust the 5-volt supply a little bit later and see if it actually makes any difference to the display, but we'll see. Anyway, so the voltage reference out and in is here, and at the top here you can see we have this differential op amp on the input circuit, and we have an input low and an input high. These two resistors that are indicated right here for the 200 millivolt panel meter, these are actually not in circuit. So you've got that's the basic scale is 200 millivolts. These two resistors show up when you have a 2 volt, 20 volts, or a 200 volt panel meter. And that's pretty much it as far as what it shows you in here. You can get a version that runs off of a 9-volt battery as well. The amount of current that I've got 2 panel meters currently plugged onto my breadboard, and they're barely drawing, the lowest resolution I have on my power supply is 1 milliamp. I haven't put a meter in series yet to see how much they draw, but it's only indicating 1 milliamp on the power supply, so it could be anything as low as just over 500 microamps to drive these two panel meters together. So a battery should last quite a long time if you used one for it. In the circuit we're going to have, we're not going to need to when we bring it into our power supply. We're just going to use a 5-volt supply, which will be a standard low voltage, standard low dropout, low voltage regulator. So that's all going to be just nice and fine. Now the benefit of having a differential input on a panel meter is that you can actually compensate for some of the wiring. I'm not going to go into any more details than that right now. Okay, so one of them is already hooked up to the DC load that I built in the last video when we were talking about power stages and things. It's not a fully configured DC load yet. All it is a N-channel MOSFET with a current sense resistor, and I'm just driving it from my power supply directly. We will have a video later on that deals with hooking up an op amp and the voltage reference as we start building this into an actual functioning unit. What I have, there's a few other things on this breadboard, but none of these are hooked up. So what I have up top here is I've got this Agilent 1273A multimeter monitoring the current that is across my sense resistor. So this is the FET current control circuitry I have, and the FET gate is configured and connected directly to one of my outputs of my bench power supply because it's a pretty accurate output and stable, so I can use it to control the gate quite easily. The other output is actually connected through this sense resistor right here, which is a 0.1 ohm 1% Vishay power resistor. So I'm measuring the current that's flowing through that. I have a blue wire that's attached at the back end here coming down to my plus sense, which is just tapped here, and then all the grounds are connected together right here. Now I'm going to change this later on, but I wanted to leave it this way, which is what a lot of people would typically do, because if you think about this unit all being inside a power supply, then this would be the equivalent of the terminal on the outside of the power supply unit, and I'm going to show you why measuring right here, it's not always a good thing. All right, so we'll get to that in a moment. And then the last piece in this puzzle right now is my Keithley bench power supply, which is providing all of the voltages. So channel 3, which is a 0 to 6 volt channel, currently now is outputting exactly 5 volts to drive the panel meters, and as you can see here, it's reading pretty much, it's only the first digit that's popped up there. The second channel is providing the supply for the current to go through my DC load, and the first channel, which is currently set, whoops, going too far here, which is currently being set at 3.069 volts, is actually just going to the gate of the field effect transistor to control the current. So it's basically a voltage to current converter on this FET right now, on the MOSFET. And with the 3.068 volts in, according to my power supply, I'm actually drawing 525 milliamps. So if I come back down to my Agilent, that was it just turning back on because it actually timed out on me. This is showing me I've got 54.6 millivolts across that resistor, which would indicate 546 milliamps, yet my power supply says 526. So I've got 200 milliamps adrift basically between what my power supply thinks I'm drawing and what my meter thinks I'm drawing. Now remember, the Vichy resistor is 1% accurate, so that doesn't account for nearly 5% inaccuracy there. Now if I go down to the panel meter on here, you'll see it actually agrees with my Agilent meter almost to the letter. So I have 548 milliamps right here. My Agilent is saying 548.5 milliamps. So I would say that that's pretty accurate. Now what's the problem here? Well, this is where having a differential measurement will come in a moment. It's actually the way this is wired up, all right? My DC load, I'm going to add some diagrams in a minute. In fact, I'll probably get some out in a moment and draw it on a piece of paper. But basically, I've got the positive supply coming in on here from my power supply, all right? So it's feeding through to the MOSFET. It's coming out of the MOSFET through the 100 milliohm sense resistor, and then it's coming down this black lead back to the common point here where everything is hooked up to for the common reading. Now you might think, well, you know, I'm drawing nearly half an amp. I've got some fairly thick, I think it's 18 gauge wire here, so it's more than capable of handling up to 10 amps or something like that. It's not very long, it's only about 6 inches long, so you know, how much volts could be getting dropped across that resistor, that piece of wire, if anything? Or is it because my Vichy resistor maybe is worse than what we think it is? Well, let's do some testing and see. Okay, so remember, my meter right now says, sorry, my power supply thinks I'm drawing 531. It's just, as it's warming up, it's just drifted a little bit. My Agilent and the panel meter both say 552. So I've still got that 200 millivolts difference. Now if I take my panel meter down here, so let's just go to the wiring right about here. I don't know if you can follow along, but it's going to be, the diagrams that I draw a little bit later will help. So I'm going to move my meter, which is this one here is a positive of both of these. Now I will tell you that it's not, I will tell you now, it's actually not a problem with this end, with the positive leads, because this is actually not involved in the current path at all. It's actually tapped off at the, let me point to it, on the DC load here. I'm tapping off at the top end right here, so it's not actually, and the only things that are on there is the high impedance input of the digital panel meter and the 10 mega ohm input impedance of my Agilent meter. So these two are not going to be the issue. But what I do have is the ground lead here. All right, I've got the power flowing through this black wire, and then it's going back up to my power supply. Now I'm basing my measurements assuming that I have a 100 milliohm within 1% resistor. All right, my power supply says I'm drawing less current than what my meters do, even though my meters are very, very accurate. And the reason ultimately for this is because I'm actually dropping volts across this short piece of wire. Now normally if I wasn't using such a low value resistor for current sensing, this wouldn't be an issue. But because it's only 100 milliohms, you know, I've dropped 100 millivolts across this, which is not a lot. But if you think about the 200 millivolts, it's only 2 millivolts that I'm dropping across this little piece of wire. And we'll do some calculations a little bit later based on the gauge and what the resistance per foot is and things of this. And you'll probably find that it's about right for 1/2 amp, that what we're losing here. So if I take my meter, which is this black lead here, all right, and I'm going to connect it now directly to the other side of the Vichy precision resistor. Now, if I look at I haven't moved the panel meter yet. All right, that's the Agilent. It's reading 5369, and that's the power supply telling me I've got 53.8. So 53.7, 53.8. I'm within 1% now, which could be the tolerance of this resistor. My panel meter is still reading 5.5 because I haven't moved it yet. So what I'll do now is I'm going to adjust that one, which is actually this little thin black wire. I'm just going to pull it out of here. And I'm going to move it to the same point now as this resistor, and hook it in there. Now, so all I've done is bypassed, get back to it. All I've done is I've bypassed this 6 inches of black wire. That's it, nothing else. All right. Now if I look at my panel meter, it says 5.4. If I look at my digital multimeter, it says 5.4, and if I look at my power supply, it is actually saying 5.4 as well. So just by making a minor adjustment of where I've hooked in my meter, I've actually changed the meter reading to be significantly more accurate. And now, as you can see, this is this little panel meter. It's agreeing with my power supply, which is within 0.1 or 0.05% accuracy for its readings. My Agilent, which again is within 0.02%, I think, accuracy, and this little panel meter is also now agreeing completely with the three. The reason for that, as I said before, when we looked at the diagram of going back to the diagram here a second, let's just zoom in on that a little bit. All right, this differential input here is what's fixed this for us. Because the panel meter is not tied to ground for its measurements, all right, even though the power supply has still got a common ground, the differential input is able to compensate for this power supply wiring that I've got hooked up here. It's not the best wiring, so please forgive that, but this little bit of 6 inches of wire, that differential input is now compensated for that voltage drop on that piece of wire. Okay. So the next thing we're going to do now is I'm going to hook up, as you noticed here, I've got two panel meters, all right? So I've got the first one now reading the current, so this is actually giving me a good indication of what the current is. If I go back to the Agilent power supply, I'll just start cranking the current up a little bit here. So power supply thinks I'm drawing 760, 771, 72 milliamps. So it's just settling down, 775, yeah. And that's all agreeing with the Agilent, the power supply, and the panel meter. If I take it up to an amp, my Keithley power supply will only actually give a maximum of about 1.5 amps. So I'm not going to worry about going too much beyond that. So my DMM says 103, the panel meter says 103, the power supply says 103 as well. So that's pretty good. And so if you think about this, that's 1 amp. So we're able to now measure on this panel meter down to 1 milliamp in resolution. For most low-cost power supplies, like for a student power supply or something, that's probably way more than enough accuracy for what you'd want there. If you don't have a precision voltage reference and slightly more expensive parts where you put in 0.1% or 1% resistors, maybe you're just using 5% resistors and things, then this is more than accurate enough for what you want to do there. So now I'm just going to now hook up the second meter. What I want the second meter to do though is I want it to be able to measure the voltage across the load that I would have. So what I'm going to do is, I've got it here somewhere, is hook up a 10 ohm resistor in series with, there it is. I have a 10 ohm resistor here. Sorry, broke the lead off. That's not going to work. I'll get another resistor that I can put in series with this load so that we can have something like pretending it's a circuit under test. So this would then be a, if this was a power stage of a power supply, we would be measuring the current flowing through it. If it wasn't, then we would be measuring the voltage drop across the power supply. So anyway, we're going to hook this up. Now because I'm running on 12 volts, I can't just hook the second panel meter straight across that because I'd fry it, because it's only a 200 millivolt input. So I've already got to put a basically a 10-to-1 divider on the input to the panel meter. So I'm just going to get that sorted out and then we'll be back in a second. Okay, don't have a bunch of precision resistors handy, but what I do have is a bunch of 100Ks, 10Ks, 1Ks, 100 ohms, and 10 ohms. So typically, if you were making something like this as a production kind of system, you would probably get a precision divider network, which companies like Vishay can actually sell you off the shelf as a single package, either in a 220 package, like TO220 kind of package, or a little PCB 3-pin mounted device or something like that. And what it is it's built as a resistor divider internally and typically laser trimmed or something like that to give you an exact 10-to-1, 100-to-1, 1,000-to-1 kind of ratios across the divider. Now unfortunately I don't have one of these at the moment. I will see if I can contact some people and see if they can send me one maybe that I can include in a later video. But for now, what I do have is, as far as my tool chest is concerned, I have a bunch of 100Ks, 10s, 1s, 100 ohms, and 10 ohm resistors. I usually keep like a decade set handy for prototyping and things like that. So if you actually chain them all together so that what you end up with is basically 111.11K in total, then if you look at this divider here, if I put in 20 volts here, if I measure here, I'm going to get 2 volts. If I measure here, I'm going to get 200 millivolts, 20 millivolts, or 2 millivolts. So I've got to divide by 10, divide by 100, divide by 1,000, and a divide by 10,000. The total impedance of this chain is basically 111K, I mean, plus obviously the digits. Now, my resistors aren't high precision ones. There's a mix of 5% and 1% resistors in here. So my divider is not going to be perfect, but it's going to be, you know, reasonably good for the purpose of the demonstration. So what we actually want for our purposes is we want to have our 0 to 20 volts in here, and we want to tap off at divide by 100 because we want to have 0 to 200 millivolts. So what's going to happen is the 0 volt will go to the negative input of the second digital panel meter, and the plus volts will go to what I'm trying to measure, and the tap off point, which is going to be at the divide by 100, will go to the positive input on my panel meter as well. Now if I just move up here a little bit to this other diagram, I've just tried to basically sketch out what I currently have. So what I want to do, if you're doing a DC load or something like that, you really would want to keep track of how much power you're dissipating in your MOSFETs or in your driver stage, because if you dissipate too much power, you're really going to you know, potentially damage the FET or something like that. And when we get to doing the actual power supply, my circuits need a complete rearrange to demonstrate the way a power supply would monitor its current. But the principles are kind of basically the same. I'd want to monitor the output volts and correct for that, and I would also want to monitor the current that's flowing through the power supply. And potentially I'd want to monitor the power that's being dissipated in my driver stage as well. So in our case, I'm just going to measure the volts across the MOSFET, so I know how much power this one is dissipating, but I can't measure the current through the MOSFET without this 100 milliohm resistor. So what I'm going to do is I'm going to measure the current the way we were just doing it across this 100 milliohm, which we've already got the first digital panel meter reading, and as you've seen, it's pretty accurate. And the second panel meter I've connected to the high end of the 100 milliohm resistor. and then the positive side of it through the divider network is connected to the top end of the MOSFET. Now I've got a 1 ohm resistor connected as well, so that I don't dissipate as much power in the MOSFET. I mean, it's not going to drop a lot of it, but my 10 ohm resistor unfortunately broke, so I can't use that anymore. I'll have to get another one. So why don't I use the same common 0 volts on the low end of this 100 milliohm resistor? Well, as you've already seen, when I start passing 1 or 2 amps through this chain here, the volts here starts to go up. So if I actually measure from this bottom point up to here, not only will I measure the volts across this MOSFET, but I would also be monitoring the volts, adding to it the volts that I'm dropping across here. Now you'll see when we go back to power supplies and things like that in a future video that if this 1 ohm represents effectively the output of the power supply, and it's just that this is effectively the output driver stage, and this is my load that I have externally, okay, which that's going to be a variable current load and things like that, you know, because different circuits and things, the current that they draw is changes and things. So this could easily represent the output, the load from some kind of circuit under test. So given that, when we want to monitor the current and the voltage for a load, if you measure down here, you're actually going to get an inaccurate reading for the voltage that's going to be coming out of the power supply here. You want to eliminate the voltage that you're dropping across this resistor, which, as I said, could be 200, 300, 400 millivolts. So if you're setting, say, exactly 5 volts on your output, and you're trying to measure the volts across your load, but you're including this resistor, then you could be as much as 10% out in high current situations, or even more. So if you take the positive side of the resistor, which is right here, and use that as the negative input for your digital panel meter stage, then as the current increases, this negative input is going to slowly increase as well. This differential input will basically, because it's not tied to ground, it will completely eliminate any voltage that's being added to this. And then the positive input, of course, is on the other side of the MOSFET, so that's going to be monitoring the volts that's across this, which would be typically what would be across your load if you were testing some kind of power supply, or you were building a power supply, and this represents the load. So how does this actually work? Well, let's go to the circuit and see. I'm not going to bother, well, I'll quickly show you my divider network just so you can see. It's not pretty. I've just quickly put it together for the sake of this prototype. So what we have here is the positive volts from our load up here comes into the top of the chain. We've got the 100K, a 10K, a 1K, 100 ohms, and a 10 ohm. And we're tapping off on the top of the 100 ohms here. So we've got basically 110K at the top, and we've got 1K, 1.11K at the bottom. All right, that gives us ideally an exact 10-to-1 divider network. Of course, with the tolerance of the resistors and things, it's going to be a little bit out. So how far out? Well, it's not too bad. Here's the reading we're getting on the second panel meter. So I'm getting 11 point, I need to adjust the decimal point on this because this is measuring volts here. So let's just tweak this. There we go. So now we're measuring volts properly, given the proper range. So we've got 11.83 volts measured at our divider network point. What I actually have coming out on the Keithley, as you can see, is exactly 12 volts. It's this one here, which is coming out right now. I'm drawing about 207 milliamps. If I come down onto my panel meters, sorry, my digital multimeters, this one is showing the current, which is 206.7, so that's pretty much spot on compared to the other ones. And my, oops, these things keep switching off. I will have to adjust the timeout for this at some point. So the second panel meter here is showing my same thing. It's showing 118 millivolts across the divider network. Now if I just move my connection to the top of the chain just so you can have something to compare to. Where's my chain gone? There it is. So if this is the second digital multimeter. I'm going to put it on the top of the chain here, just so you can see. All right. So now I'm reading the 11.83 on my panel meter, and I'm reading 11.9. So 11.8, 11.9. It's within 1%. So I mean, it's not too bad a little thrown together divided network. Anyway, back to the panel meters. So let's just go back down here now. So as I said, two little cheap panel meters. These panel meters are both identical. They both have a range of 0 to 200 millivolts, plus and minus. And as you can see, now one of them is configured to measure voltages, and the other one is configured to measure amps, and it's like at the moment 208 milliamps. Now, I've set a limit on my power supply of 1 amp maximum load. So if I start to increase the gate drive on my MOSFET, I'm going to increase the current here. So you're going to see the top one is slowly increasing. Now my volts are still the same because my power supply is able to drive it. Now, because I'm drawing I'm drawing less than what the power supply is able to provide at the moment, all of this voltage is actually being dropped across the MOSFET. So the more I increase the current drive, all right, so if I go up to say 500 milliamps, now I've got just over 500 milliamps being drawn through my MOSFET, and I've got 11 volts across it. Because remember my circuit here, I'm tapped directly across the MOSFET measuring the volts. So that means that 12, almost 12 volts at just over 500 milliamps, that's basically 6 watts of power. And if I stick my finger on the, go over here, it's starting to get a little bit warm. It's not too warm yet because I've only just cranked it up. And of course, if I start increasing this even further, so that I go up to say 1 amp, there we go, 1.01 amps. So I've got 11.75 volts. All right, my power supply has been configured, I think, to current limit at, let me just see, 1.2 amps, where the volts would start dropping. So now I've got basically 12 watts being dissipated on this MOSFET. Now it's not going to get, it is starting to get warm to the touch. Nothing that I can't keep my hand on, because if you look at this, this one here, by the way, is I'm only tapping off the 1 ohm resistor. The other heatsink is being used to dissipate the heat from the MOSFET. So it's a pretty big heatsink. The MOSFET's capable of over 300 watts on its own, and being able to get up to 100 and I think nearly 200 degrees centigrade. I'd have to check the spec sheets again. So we're nowhere near damaging what the MOSFET can do, but it is certainly starting to get a little bit warm there. All right. Now if I start increasing this again, so if you think about the fact that if this was an external circuit you were testing, at a certain point, we would want to go into constant current mode. So if I increase the gate current now, all right, we're at 1.1 amps, 1.2, I'm just flipping into constant current mode. So now, as I start increasing the current, you can see that I'm staying basically at the 1.2 amps because my power supply is now limiting it. But because I'm turning the MOSFET harder on, then the volts across it is dropping, and the output volts, of course, on the power supply is correspondingly dropping. So this is behaving the way it should, of course, because I've got now less volts being delivered out from the power supply. So this circuit is a great, right now, this in itself could effectively be a DC load, just controlled by a couple of potentiometers, well, one basically onto the MOSFET to set the current. You would just have to crank it to get the current you want, and it's going to show you in real time what that current is. If you wanted to make it more precision, where you can set the current before you have anything connected, well, then what you'd have to do is have some op amps and a voltage reference and know the characteristics of the feedback circuit. So you would have a voltage reference of, say, 200 millivolts precisely, and you would then have a feedback because you've got this 100 milliohm resistor. At 2 amps, you would have exactly 200 millivolts coming back in. So you could easily use that voltage reference to be a driver. The op amp would allow you to compensate for the fact that you had the field effect transistor as a control mechanism and your 100 milliohm resistor in the circuit as well. And you would basically be controlling 0 to 200 millivolts on the op amp, would give you 0 to 2 amps onto your load. But for the moment, we're really focusing on the use of these low-cost digital panel meters to give us a reading for the power supply. So as you can see, going back down to the panel meters now, they're giving you some quite good accuracy. If I just pull the specs out again, and I'm just going to quote from what this says the accuracy is supposed to be. Where is it? So the high accuracy, plus or minus 1 count, plus or minus 0.05%. I think for that, it's it's an easy fix for a basic power supply. I mean, you can get cheaper panel meters that don't have quite the same accuracy, and in some cases that'll be good. But if you want an analog controlled power supply or DC load, or we're going to do a power meter, a DC load, and a dual channel power supplies, then at the low end of the market with reasonable accuracy, something like this would work perfectly. So anyway, I'm not sure what else I can show you as far as the panel meters are concerned right now. I think what I've touched on through this video too is the fact that your wiring, if you're not careful where you connect things, can actually mess up your readings. And it's important that you be aware of where you put your connections for both your voltage readings and your current readings. For instance, right now, I'm passing 1.2 amps through this. My panel meter, the 0 volts, is, as I showed you on this circuit here, is put on the top end of this here. So across this 100 milliohm resistor, we basically got 1.2, so 120 millivolts, all right, being dropped across this thing. So the volts read 3.8, so 300 odd millivolts. If I change the ground for this, which I'll do right now, if I can find where I put it. I'm going to try and shift the ground for that's for the voltage divider. Where's the current one? Oh, here's the current one here. That's the plus for the current. This is the negative for the current. So right now it's on the other side, directly on the resistor there. I've taken it off, so it's going to be floating around a little bit. But what I'm going to do is I'm going to connect it to the same ground as pretty much everything else is connected to. And you'll see what a difference it makes. All right. If I connect it to the I'll keep blocking things here. I connect it directly to the side of the. All right, I'm reading 1.2 amps there, and if I move it to the other end of the piece of wire here, 1.247, 1.208. So you can see just that little piece of, and it's no more than 6 inches of wire. I'm just shifting the position of it, and it's changing the reading considerably. Now if I take it to the other end of the sense resistor, so I'm on the completely on the 0 end of the power supply, if I can find it. Oh, that's what I was on here. This is on the 0 end of the power supply. All right, so I'm now measuring the wrong current. Now with the voltage, okay, let me just put this one back on the current supply. Excuse my arm blocking things a little bit. So as you can see, for the current measurement, it's important that you tap off the right places. For the voltage measurements, if you want to eliminate the current effect on the current sense resistor, again, it's important that you connect to the right point. Okay, I just want to show you what happens when you connect your meter in 2 different places. If you remember, on our diagram here, I've got the negative connected to the positive end of the current sense resistor that goes into the voltage sensing. So we're measuring directly across the FET. I'm going to show you firstly with the digital multimeter the difference. I've got 1 amp going through this load right now roughly between measuring across these 2 points for the FET and measuring across here. A lot of lower end power supplies measure directly from the negative 0 volt rail to the top end of the output of the power supply and doesn't compensate for any drops across this sense resistor. So if I just bring it up to the multimeter right now, all right, so as you can see there, I've got 1.02 volts getting dropped, 1.02 amps being drawn through the circuit, and I've got 10.885 volts that I'm sensing. Now what I've got right now is my multimeter is connected to from the 0 volts, if you remember on here. So my multimeter is actually connected from the 0 volts to this point on the FET, which is what I was talking about that a lot of power supplies when they're measuring voltages will do. And I'm just going to shift it now to the top side of the FET. So what you'll see is there'll be no, top side of the sense resistor. There'll be no difference in the current. So it's 1.03 amps. I'm just disconnected it now. I'm just going to connect it to the top end of the sense resistor. So there you go, 10.77 volts. And I'll go back to where it was, 10.87. So we're dropping basically 100 millivolts we're reading out, which in the case of 10 volts or 12 volts, that represents pretty much 1% inaccuracy, and that's just with a 100 milliohm sense resistor. Obviously if you have a higher one or you have higher currents, that's going to get even worse. All right, so for every amp that you put through, if you've got 100 millivolts per amp, then you're going to increase your inaccuracy by 100 millivolts. So by putting it on the top end of the current sense resistor, which requires having a differential input, you eliminate the errors. So let me just put that back. So right now my panel meter is connected to the top end as well for the voltage one here. All right, so the current sense is the top one, 1.04 amps right now. The bottom end is measuring the volts, so that's 10.6. Like I said, my divider chain is not quite accurate, so the DVM is measuring 10.7, this is measuring 10.6. Now I'm just going to turn the power off while I just rewire this to be on the other side. I'm going to shift the ground wire of the voltmeter to the other side as well. So remember, this is 10.6 right now. Multimeter is now connected. I'll put the power back on. Alright, so now that I've moved it, it was 10.6 before, now it's 10.78. So you can see that's quite a difference. So I'm going to try and, without blocking the camera much, if I can, I'm just going to take this wire out and just shift it manually between the two, see if, as long as it doesn't mess up the, yeah, it's decided to make the displays go a bit wonky. I found with these displays that for some reason if you start messing with the ground wires, I guess they're just getting into a funny state with the logic inside of them. They don't like being moved. Like right now I put them back on, I have to turn the power off to make them go back into the working state again. So you can see 1.065 volts there, and if I move it to the other point, 1.075. So it's definitely, by putting it in the correct place, which of course is over here on the top of the sense resistor, you've completely eliminated that offset due to the current through the sense resistor throwing off the output volts. Anyway, I think that pretty much covers using these panel meters and the fact that differential input ones are pretty good. There are limitations that the differential input can't go more than 2 volts away from the 0 volt line. So you have to be aware of that in order to protect them. But typically if you're using something like a 100 milliohm shunt current sense resistor, then you're never going to have an issue with that. You can put the voltage one sitting on the positive side of the current sense meter, and the current one obviously is sitting directly across the current sense resistor, and it all works quite happy. The only reason these displays were getting upset is because I was pulling wires out, and they were probably floating all around the place and getting the logic screwed up inside them. So a quick power cycle just fixed that. But I think that pretty much covers it. The next video we're going to start actually putting things all together to make a working solution. I think the first thing we'll probably do is create a DC load, because as we start going through the power supply project, you will want to be able to load up the circuitry and test how well it works and things. So that might be a convenient way to get an op amp, a voltage reference, power stage, and a meter all working at the same time. Okay, anyway, we'll see you next time.